Okay, we can take those two equations and put them together. So the entropy change in the universe is the system plus the surroundings. The change in entropy in the surroundings is negative delta H cis over T. So we can say that we could do this. Delta S universe is equal to delta S system plus delta S surroundings. Delta S surroundings is negative delta H for the system divided by the temperature. Actually, I think this is supposed to be up there. And thankfully, I gave myself a hint. Multiply by negative T. So if we multiply by negative T, we're going to get negative T delta S for the universe is equal to negative T delta S for the system plus delta H for the system. So just changing the order here so we're not starting with a negative. So now we can drop the cis subscript and just understand that any quantities without subscripts refer to the system because we took the surroundings out of it. So negative T delta S for the universe is equal to delta H minus T delta S. New fun thing, Gibbs free energy. GE is equal to H minus TS. H is the enthalpy, T is the temperature in kelvins, S is the entropy. So if we look at the change in Gibbs free energy at constant T, we would have H final minus TS final minus HI minus TS initial. H initial minus TS initial. Or delta H. God, somebody just shoot me. Minus T delta S. So the change in Gibbs free energy is the change in the enthalpy minus the temperature times the change in the entropy. The change in Gibbs free energy for a process occurring at constant temperature and pressure is proportional to the negative of the change in entropy for the universe. And that proportionality constant is negative temperature. So delta G is also a criteria for spontaneity. It's sometimes called chemical potential. is analogous to mechanical potential energy. You know, you hold something up, you know, above a surface, and it has potential energy because when you release it, it spontaneously falls down, right? So delta G is the equivalent of that, but in chemical energy. So chemical systems are going to tend towards lower Gibbs free energy, just like a falling object tends toward a lower surface, lower potential energy. And because this is, if the change in entropy for the universe is negative, then delta G will be positive. If delta S is positive, delta G is negative. So positive delta S is spontaneous for the universe, right? So positive delta S gives us a negative delta G. So if delta G is less than 0, we have a spontaneous process. And honestly, the only way to have a shot at keeping these things straight is to be able to talk to yourself. I just talked myself through it because it was looking backwards to me. So delta G can be calculated only looking at the system, which is nice because trying to deal with the surroundings is very difficult most of the time. So all we need to know is the change in enthalpy for the system and the change in entropy for the system. So here we're looking at how the Gibbs free energy determines the direction of spontaneous change. So we have an equation where we've got nitrogen and hydrogen combining to form ammonia. Over at all reactants, pure N2 and H2, the Gibbs free energy will be at some level. And at pure NH3, the Gibbs free energy will also have a particular value. The reaction will come to equilibrium, and where it comes to equilibrium, Q for the reaction will equal K. So over here, spontaneous forward reaction, because Q is less than K. Remember what Q is? That's the reaction quotient. It's the equilibrium constant, but with current conditions. So if we only have reactant and we have no product, of course Q is going to be a very small number, and so this will be spontaneous, and it will go until Q is equal to K. Over here, having all products, no reactants, Q is a very, very large number, and so the reverse reaction will be spontaneous, and it will continue until Q is equal to K. So we see this point, this minimum in free energy is the point of equilibrium. So a couple of different cases. We have a negative delta H and a positive delta S. So entropy is increasing and the enthalpy is decreasing. So this would be an exothermic reaction with a positive change in entropy. So delta H is negative. Because delta S is positive, this term, negative T delta S, will contribute to negative, and delta G will be negative at all temperatures. Does that make sense? We're not actually calculating delta G, we're just looking at the sign of delta G. So if delta H is negative, here we have a negative minus a positive, that's going to be more negative, right? Delta G is negative. So spontaneous at all temperatures. Delta H is positive, delta S is negative. So delta H is positive, this would be an endothermic reaction and a negative change in entropy. So a positive minus a negative makes it more positive. Delta G is positive at all temperatures. So this reaction is not spontaneous at any temperature. Case 3, both delta H and delta S are negative. The delta H is negative, meaning this is an exothermic reaction, and we're also getting a negative change in entropy. This one's going to depend on the temperature. So delta H is negative, and delta S is also negative. So subtracting that negative number is going to cause this to move towards 0. So a larger T is going to increase delta G. So delta G will be positive at high temperatures and negative at low temperatures. And an example of a process like this is water freezing. Because when the water freezes, right, the entropy decreases. So we have a negative change in entropy. That will happen at lower temperatures. It won't happen at higher temperatures. What if they're both positive? Now it's an endothermic reaction with a positive change in entropy. Again, it's going to depend on temperature, and the dependence is the opposite. It'll be positive at low temperatures and negative at high temperatures. So liquid water evaporating into a gas. Delta H is positive, it requires energy to be put in. And going from a liquid to a gas, we have a positive change in entropy, right? So this will be positive at low temperatures, meaning not spontaneous, and it will be negative at high temperatures, spontaneous. So the sign on delta G matches with delta H, not with delta S. Sorry, this is how it is. So if delta H and delta S are opposite in sign, we can tell whether it's spontaneous or not at any temperature. But if they are the same sign, whether it's spontaneous or not will depend on the temperature. Consider the reaction. Calculate delta G at 25 degrees Celsius. Determine whether the reaction is spontaneous. Does delta G become more negative or more positive as the temperature increases? So I don't know if you remember looking this up in 1A, but in the appendix at the back of your book, there's several pages of tables that give heats of formation for lots of different compounds. And there's two other columns that give delta G and delta S. And this is where those come in, right? So we're supposed to calculate delta G at 25 degrees Celsius. Well, what's the equation? Change in enthalpy minus T times the change in entropy. So we've got negative 137.5 kilojoules. So I'm just going to put kilo as times 10 to the 3. Minus, gosh. And here, the units on delta S give us a clue. We got to put that in Kelvin. So that's 298 Kelvin times negative 120.5 joules per Kelvin. The Kelvins cancel out. So delta G is negative 102 kilojoules. Is it spontaneous at this temperature? Yes. So this is one of the answers. Determine or calculate delta G. The next answer is yes, it is spontaneous. What happens to delta G? Delta G. What happens to delta G? I don't know. I don't think my G is doing very well today. What happens to this delta G as T gets larger? It's going to get more positive because we're subtracting a negative number. So the bigger this gets, the more positive delta G becomes. Delta G is more positive at high temperatures. Any questions?